Hi guys, welcome to our new material video for this week. We will be starting chapter 15 this week, which is on kinetics. And guess what? This is our last chapter that we're going to do this year. It's not the last chapter of the book. The book does have 16 chapters, but we're not going to get to chapter 16. If you love chemistry, if you want a career in chemistry, if you're going to go on to college for chemistry, I'd encourage you to read that chapter. But as a class, we're not going to be doing that chapter. So today, as I said, we're starting on chapter 15, which is titled Kinetics. Okay, so we've already learned that spontaneous reactions, once they're started, will keep going. Okay, we learned that last chapter. So nothing new there. But it is important to know that not all reactions happen at the same pace or at the same rate. So some reactions happen very quickly, some reactions are very slow. Okay, so let's take, for example, we keep talking about burning paper, and that my paper doesn't spontaneously start flaming up right now because the temperature isn't right. But as soon as we raise the temperature enough and get those molecules colliding, the paper will start burning, and that's a spontaneous reaction. And if we started this paper burning, it would burn pretty quickly. Okay, so it would have a pretty fast rate. It would release a lot of heat and energy. All at once. Okay, and if we burned enough paper, we could probably even, get some like water boiling over it and things like that. Well, let's compare that to something like the process of rusting. So rusting is a chemical process, but it happens very slowly, and you've probably seen something rust over time, and you actually can't see it happening because it's happening so slowly. But when something starts rusting, you do notice it. Okay, so this releases energy very slowly over time. Okay, and obviously you would never be able to get water to boil over something rusting in the amount of energy, the small amount of energy it releases over time. But the interesting thing about these two processes, these two chemical reactions, is that the delta H's, the change in enthalpy of these, really aren't significantly different. Okay. When the reactants are used up really quickly, obviously, as I said, the energy is produced quickly, and then vice versa. When the reactants are moved up slowly, the energy is produced slowly. So each of these may produce the same amount of energy overall, but that energy is released at different rates, and that's what kinetics is all about. Okay, so kinetics is the study of chemical reaction rates. Okay. So we're all familiar with this term rates. You guys, I think most of you are driving by now. Mile per hour. Okay, you're all familiar with this rate, even if you're not a driver yet. Mile per hour. Okay, it's how many miles or the distance that you can travel in a certain time period. So we're familiar with these rate things. In chemistry, when we measure rate, we measure the concentration of something, or actually the change in concentration over the change in time. Okay? So one common unit for the rate would be like molarity per seconds. So again, we're familiar with rates, something like mile per hour. But instead of distance, we're using concentration. What's one way we measure concentration? Molarity. Okay, so we often see rates as molarities per second, or molarity over second. Now, if we have a reaction, A plus B yields C plus D, okay, where A, B, C, and D are molecules. We could restate this rate. Again, we said it was the change in concentration over the change in time. A way to write that in kind of shorthand would be the change in one of those molecules' concentration over the change in time. So what I wanted to show you is these brackets indicate concentration. Okay, so in this chapter, when we see these brackets, that means the concentration of this particular molecule. Okay, and then remember, this change in concentration would equal the final concentration of a molecule or reactant or product minus the initial concentration, because just like everything else, change in is always final minus initial. Same thing for change in time. It would be the final time minus the initial time. And usually when we're timing something, the initial time is 0, okay? When calculating this rate, the rate will always be positive. Okay, we're not going to have a negative rate of something. All right, so to make this always positive, what we do is we always calculate the rate based on the concentration of one of the reactants. Okay, so we always calculate the rate based on one of the reactants. So what this means is that, well, let me back up. As this chemical reaction happens, let's think about what happens to the concentrations of A and B versus C and D. So as the chemical reaction progresses, the concentration of the reactants, decreases. And the concentration of the products increases. Okay, so as this chemical reaction happens, the concentration of these is going to decrease. The concentration of the products is going to increase. I mean, it makes sense. In the beginning, we don't even have any products before these two things have reacted, right? So their concentration starts at 0 and then starts increasing. In the beginning, all we have is reactants, but as they're used up and converted into the products, the concentration of the reactants decreases. Okay, so if we're calculating the rate based on a reactant, we have to put a negative sign in front because the change in the reactant would be negative. This negative of a negative will make the overall rate positive. Okay. Now, there's certain conditions that will affect the rate of a reaction. And some of these I think will make sense to you. So what affects the rate of a reaction? Okay, well, one thing that affects it is the concentration of the reactants. So the rate is proportional to the concentration of the reactants. So what does that mean, that it's proportional? That means if the concentration increases, then the rate increases. They move in the same direction. Vice versa, if the concentration decreases, then the rate is going to decrease. Okay? So the more concentrated the reactants, the faster the rate will be. All right, the concentration or the rate is also proportional to the surface area of the reactants. All right, so again, proportional. So if the surface area increases, then the rate increases. Okay, what's an example of this? In several of our reactions, we've used chemicals in a powdered form, or maybe they're in crystals and we've had to kind of shake it up or break up those crystals to be a powdered form. Well, the reason we do that is because when we break solids into a more powdered form, their surface area increases. So there's more collisions that can happen when the surface area is increased, and that will increase the rate of the reaction. Okay, the third thing then is that rate is proportional to temperature. Okay, and again, if the temperature increases, then the rate will increase. Okay, so by saying proportional, that just means they move in the same direction. If the temperature goes up, then the rate is going to increase. If the temperature goes down, the rate will go down. Okay, so hopefully those things make sense to you. Okay, we're going to talk about this collision theory in a little bit more detail. We touched on collision theory in the last chapter when we said that the molecules and atoms have to collide violently enough with each other to interact with each other. And we even talked about it in terms of the burning paper, that the reason this paper isn't burning right now at room temperature, even though the paper is obviously here and oxygen molecules are obviously in the air, is because the paper and the oxygen molecules are not colliding violently enough to cause a reaction. When we add heat, that makes the air molecules and the molecules in the paper move more quickly, and if we add enough heat, then the reaction will happen. Well, the collision theory says that a chemical reaction will occur when the reactants collide with enough force that allows their electrons to be rearranged. So a chemical reaction will occur when the reactants collide violently enough that their electrons can be rearranged. Okay, so going back to this generic chemical equation, A plus B yields C plus D. A and B will not actually react with one another unless they can collide. These molecules can collide violently enough that Let me start over. A and B will not chemically react unless these molecules collide violently enough that their electrons are actually moved around. And when those electrons are moved around and everything starts moving around, then things bond with different things and we end up with our products C and D. So let's talk about this even in a little bit more detail. Remember the structure of an atom. So atoms have a nucleus, and in the nucleus we have protons and neutrons. And then around the atom's nucleus we have clouds of electrons, okay, with their negative charges. Okay, and there's different shapes for these clouds and whatever that we've studied. But we have the nucleus with the protons and neutrons. The electrons are out on the outside. Well, as atoms get close to each other, their electron fields are negatively charged and they repel each other because they have like charges. So if I have another atom here with its electrons, these two are going to repel each other, because the outermost charge here is negative, the outermost charge here is negative, and like charges repel. Okay, so if we look at the picture on page 458, so if you, well, I guess I can just put my book in front of the camera here, and we can talk through this picture. We're looking at a reaction, this reaction here, between carbon monoxide and nitrogen dioxide. And if these two react, they will create carbon dioxide and nitrogen monoxide. This is just a single displacement reaction. There's one oxygen leaving the nitrogen dioxide and moving to the carbon oxide to make carbon dioxide. Okay, so the only thing moving is one oxygen is moving from here over to here to give us our two new products. Well, for the reaction to take place, for this reaction to actually happen, the carbon must collide with the oxygen, okay? And the only time that actually happens is in this last example. So let's look here. What happens? We have our carbon monoxide, and our nitrogen dioxide. And what happens here? The two oxygen atoms, which are these red ones, the two oxygen atoms are actually the ones colliding. Well, they repel each other, so nothing happens. We end up with the same two molecules that collided. This is called an ineffective collision because nothing changed. It didn't cause this reaction to take place. Let's look here. We have the carbon and the oxygen reacting again with the nitrogen with the two oxygen, except this time the carbon's oxygen is reacting or is bouncing off of or colliding with the nitrogen atom. Well, these two must not be very attracted to each other. So again, nothing changes. Finally, the carbon monoxide molecule has realigned itself, or its placement is a little bit different, so that its carbon atom is hitting one of the oxygen atoms from the nitrogen dioxide. Well, as soon as this collision happens, where these two atoms actually collide, we get our chemical reaction. And this oxygen stays with the carbon monoxide to become carbon dioxide. This is called an effective collision. An effective collision will actually cause the reaction to take place. Okay, and all of this is part of what we call collision theory. The first two collisions are ineffective because they don't cause the reactants to become the products. The reactants collide and they just stay the reactants. The reactants collide, they stay the reactants. This is an effective collision because as the reactants collide with each other, they're aligned properly to allow the carbon monoxide to gain this oxygen atom and become carbon dioxide, and for this to become nitrogen monoxide. Okay, so now let's think back to our rules. When I increase the concentration, or to the things that will make the rate go faster, when I increase the concentration, I get more of these effective collisions because there's more reactants. The reactants are more crowded. So these are we're gonna get more effective collisions. When I increase the surface area, again, we're going to get more effective collisions because there's more of these reactants exposed all at once. And then finally, when I increase the temperature, I'm also going to get more effective collisions because the molecules and atoms are moving around faster, so the collisions are going to happen more frequently. So the more frequently they happen, likely will get more effective over time. Okay, so hopefully that makes sense. This is the collision theory. All right. Okay, we're going to move on and start talking about the rate equation. So there's actually an equation that can be used to predict the rate of a chemical reaction. Okay, and it's called the rate equation. Okay, and as I said, it can be used to predict the rate of a chemical reaction. So if we have a chemical reaction where we have, well, let me write it out first. This is a C. Okay, so we have this number of moles of molecule A, this number of moles of molecule B. These are the reactants, and they will yield this many moles of molecule C plus this many moles of molecule D. Well, the rate of this reaction, we would say, equals K times the concentration of my first reactant raised to the X times the concentration of my second reaction raised to the Y. So let's talk about what some of these things are. Okay, K is called the rate constant, which is a little misleading because even though it's called the rate constant, it's different for every reaction. Okay, and sometimes the units even change. All right, so even though it's called a constant, it's actually different for every single reaction, and sometimes the units even change, and we'll see this as we go. Now, A and B are in brackets, so we know that means the concentration of A and the concentration of B. But what are these little exponents? Well, these exponents are called the orders. Okay, and in this case, these orders, there's a certain verbiage. If we would say, like, if X equals 2, then what we would actually say is that what we'd actually say is the second order with respect to A. Okay, so this phrase, second order with respect to A, means that for concentration A, X is 2. All right, let's look at another example. If Y equals 1, we would say the first order with respect to B. Okay, so these exponents, we call them orders. If the exponent is 2, we say it's the second order. If the exponent is 1, we say it's the first order. If the exponent would be 5, we would say it was the fifth order. Okay? Now, one thing to note here is these orders have nothing to do with the number of moles. Okay? So x does not equal little a. Y does not equal little b. They're really not related to the coefficients in the chemical equation. They're a thing of their own. Okay? So this is the order with respect to A. Y is the order with respect to B. The overall order for the reaction is equal to x plus y. Okay, we just add the exponents and that gives us the overall order for the reaction. So in our example, if x equals 2 and y equals 1, the overall order would be 2 plus 1 would be 3. Okay, and we're going to see examples of all this. So don't worry if we're not making total sense or if this isn't totally sinking in quite yet. So actually, let's look at an example right now. Example 15.1. Okay, we have the following chemical equation. 2 hydrogen gas plus 2 nitrogen monoxide gas yields 2 water vapors plus nitrogen gas. Okay? And what are we told here? The reaction below is of first order with respect to the H2. Okay, so this is first order. And second order with respect to the NO. So this is second order. We're told that in the problem. When the concentration of H2 is 0.012 m, so this one is 0.012 molarity, and the concentration of the nitrogen monoxide is 0.045 molarity. The rate of the reaction is, so it tells us our rate, 3.41 moles per second at 25 degrees Celsius. All right, so there's two questions. We'll take the first one first. What is the rate constant? Okay, well, let's think back to our rate equation. So the rate equals K, the rate constant, times the concentration of the first reactant raised to its order times the concentration of the second reactant raised to its order. So let's rearrange this equation for K. Okay, so just algebraically then, I would divide both sides by this to get K by itself. So K then is the rate divided by concentration of A to its order times concentration of B to its order. I just divided both sides by this. Well, now I know all these four values, so I can just plug these things in. The problem told me the rate is 3.41 moles per second. My first reactant is the H2, and the problem told me its concentration. So 0.012 molarity, and it said it was the first order, so that means that little exponent is a number 1. It told me the concentration of my second reactant is 0.045 m, and it's of second order. Okay, so when we put the numbers in, you can think of these brackets just then as parentheses. All right, so this would equal 3.41 moles per second over, well, anything raised to the first power is itself. So this is 0.012 m. Okay, and then this, I just square everything. So this becomes, oh shoot, I don't have this math done out. So it becomes 0.045 squared times m squared, because remember, we square the number and we square the unit. All right, so in the end then, I can simplify this even more. The numerator stays the same. If I multiply these things out, the numbers, I get 0.000024. And my unit, I have 1m times m squared. So my unit here is m to the third. So now this can also be simplified. 3.41 divided by 0.000024 would be 140,000. But let's look at our units. I have, my units are moles over seconds times moles cubed. So moles over seconds, and then in the numerator, I have another moles cubed. So these two can simplify. If you remember back to algebra, I have 1m here, I have 3 m's here. So this cancels out, and instead of m cubed, I end up with m squared. So all I have left in the numerator then is 1. All my variables have gone away. So the unit for this then is 1 over m squared seconds. So if you don't understand this, there'll be other problems that you can look at and do on your own, but this is just algebra. Hopefully you know this from your algebra class. All right, so this then ends up being our rate constant. So our rate constant is 140,000, 1 over m squared seconds. The second part of the equation was, what is the overall rate? I'm sorry, not overall rate, the overall order of the reaction. Well, the order for my first reactant is 1. The order for my second reactant is 2, so I just add those together, and the overall order for the reaction is 3. Okay. Let's look at another example. It's actually the second part of this same example, 15.1. We have an equation. Again, H2O2 aqueous plus 3 iodine ions in an aqueous solution plus 2 hydrogen positive ions in an aqueous solution, and that yields I3 ions plus water. Okay, and the problem tells me that this is first order. This is first order. And this is the zero order. Zeroth order, okay? And it also tells me the concentrations. My concentration here is 0.010 molarity. This is 0.020 molarity, and my hydrogen ion is 0.00050 molarity. Okay, it furthermore tells me that the rate is 2.30 times 10 to the minus 6 moles per second. So again, we want to find the rate constant. Okay, so let's do what we did the last time. The rate equals the rate constant times, this time we have 3 products, so let's put our first one in, 0.010 molarity, and that's the first order. Okay, we'll solve this one a little bit differently instead of rearranging the equation first. The second one is 0.020 molarity to the first power because it's the first order. And my third reactant is 0.00050 molarity to the 0 power because it told me it was the 0th order. And it also told me the rate, so I'll just go ahead and write that in over here. The rate is 2.30 times 10 to the minus 6th moles per second. Okay, so do you remember from algebra when something is raised to the 0 power, what that equals? This equals 1. Anything raised to the 0 power equals 1. So let's simplify this a little bit. On the left-hand side, I have 2.30 times 10 to the minus 6 moles per second. That equals K. Well, this is raised to the first power. Anything raised to the first power is just itself. So this becomes 0.010 molar. This, again, is raised to the first power. So it's 0.020 molar. And again, anything raised to the 0 is just 1. Okay? So we can simplify this even further. We can rearrange the equation to get K by itself. So we would divide both sides by those factors. That means we would divide this side by those same factors. Okay, and if we do that, these cancel out. We're left with K by itself. And if we do this math out, we end up with 0.0115. And what are our units? Let's think about our units here. This mole is canceling out this mole. The seconds is in the denominator, so we end up with 1 mole times second. Okay, so this is a good example. If we look at our last problem, the unit was 1 over mole squared second. Now our unit is 1 over mole second. So this is where I said the mole constant can even have different units. In this case, the molarity is squared. In this case, molarity is not. Okay, let's see, what is our overall order for this equation, or for this reaction? Well, it equals all of our orders added up. So first order, 0th order. So the overall order for this reaction is 2. So you might see a pattern here. If you find the overall order for the reaction, the molarity in the denominator here, its power is always 1 less than the overall order. So the overall order here was a 2, so its power is 1. If we look back at this example, the overall order for the reaction was 3, so the power on this molarity was 2. It's always 1 less than the overall order of the reaction. Okay, so the units depend, these units depend on the order of the reaction. Okay. So when we talk about this reaction rate, the rate of the reaction is actually instantaneous, so it's only good for a moment in time. So the reaction rate is instantaneous. So it's only good, or maybe we should say only valid, for a moment. And then it changes. So why is that? Well, as the reaction proceeds, remember we said the products will be used up and their concentrations will become less. I'm sorry, not the products, the reactants. Let's just write out an equation. As this reaction happens, the concentration of these products continues to decrease. These products become less and less. They're being used up to make the products. Okay? So the fastest the rate is at the very beginning of the reaction, and from then on, the rate continually decreases. Okay? So when we're using that rate equation and putting in the molarity of our reactants, those molarities are continuously decreasing, which then is continuously decreasing our reaction rate. So we can measure it for a moment in time, but as soon as we calculate it, then it's changed. Graphically, we could show this. If this is the reaction, as the reaction progresses, this is the reaction rate. So at the very beginning of the reaction, the rate is going to be high, and then as the reaction progresses, the rate is going to get lower and lower. So over time, as the reaction progresses, the rate starts out high and becomes slower. He goes into this discussion that technically reactions never really end, but the concentration of the reactants gets so small that we can't measure them anymore. So that's all kind of theoretical, but okay, so let's move on. So where do these reaction orders come from? Those exponents, those are called the reaction orders. Where do they come from, and how are they determined? Well, we've learned that those exponents, or those orders, don't really correlate to the number of moles or molecules, so they don't come from that. But we can figure them out by examining the rate of a reaction with different known concentrations. So the best way to really illustrate this is to look at another example. Okay, so this is example 15.2 on page 462, if you're following along. All right, we have an equation or a reaction. Hydrogen gas is reacting with nitrogen monoxide, and it's creating dinitrogen oxide gas plus water vapor. Okay, and let's say we run this reaction using 3 different trials with 3 known concentrations. Okay, so the book creates this table, trial 1, 2, and 3. We're going to put the concentration of our first reactant in this column, the concentration of our second reactant in this column, and the instantaneous rate that we measure. Okay, so for trial 1, I have 0.030 moles. For trial 2, 0.30 moles. And for trial 3, 0.60 moles. The nitrogen oxide, trial 1, 0.30 mole. Trial 2, 0.60 mole. Trial 3, 0.30 mole. And then I have some different rates over here. Okay, so I've run this reaction 3 different times using 3 different trials. I know my concentrations of each reactant and I know the rate. Okay, so given this information, we can determine the rate equation, including the rate constant and the orders. So first, let's look at the orders. How do we figure those out? Okay, well, so to figure those out, I'm going to choose 2 of my trials and plug the values in to the rate equation. Okay, so remember, my rate equals K, and in this case, it'll be H2 raised to its order plus NO raised to its order. So let's just pick trial 1 and trial 2. Okay, and for a reason you'll see in a minute, I'm going to write trial 2 first. Okay, so my rate on trial 2 is 0.00972 molarity over second equals my concentration here raised to the X, because I don't know the order. Sorry, it also has a K in here. And then my other reactant raised to the Y, because I don't know my order here. Now I'm going to choose trial 1 and write the rate equation for trial 1. Put in what I know, the rate 0.00243 molarity per second equals K. This is 0.30 molarity. I don't know my order again. 0.30 molarity, and again, I don't know my order. So I have both my trials listed. Now what I'm going to do is I'm actually going to divide these 2 things. And what you'll notice when I divide is a lot of things fall out. My rate constant, my K, falls out. I have 0.30 m to the X over 0.30 m to the X, so it cancels out. Okay? So what I end up with then is on the left side, well, and these units cancel out as well. So what I end up with on the left side is 0.00972 divided by 0.00243. And if I do that, well, let me just write it out actually. So over here, I end up with this over this number. My units have canceled. My K has canceled. My concentrations here have canceled. And so I end up with 0.60 molarity to the Y over 0.30 molarity to the Y. Okay, so if I do this math, I get 4.00. And then remember, if I have 2 things both raised to the same exponent, the numerator and the denominator both raised to the exponent, the same exponent, I can combine those as such. Okay, if these 2 items, the numerator and the denominator, are both raised to the same exponent, I can combine them raised to the same exponent. Well, now these molarities cancel out. Okay. So 0.3 or 0.6 divided by 0.3 is 2.0 raised to the Y. What do you need, Luke? Can you take that down to the Dixes? Thank you. It's okay. Okay. Okay, sorry for that. I needed to talk to my son for just a moment. Okay, so now we can just think to ourselves, well, what power can I raise 2 to get to 4? Well, in this case, y must equal 2 because 2 to the second power equals 4. So I have found my first order. Okay, so the order for, now remember this was Y, which was our our nitrogen oxide. Now we know this is second order. All right, let's try to find our order for the hydrogen. Okay, let me clue you in about why I wrote trial 2 over trial 1. First of all, when trying to determine these orders, we need to look for trials and find 2 where one of the concentrations will cancel out. So when I chose trial 1 and trial 2, I noticed that the hydrogen concentration was the same. So when I do the division, those 2 are going to cancel out. The second thing I want to do is I want to divide the larger number by the smaller number. Okay, the numbers will just come out easier. You can do it the other way, but then you're going to be working with fractions and it's going to get more complicated. So look for 2 trials where the concentrations will cancel out when you divide, and then always divide the larger by the smaller. Okay, so to determine, let me just do this. I want to keep my equation up here. Okay, so what 2 trials would be good to use to try to figure out the order of the hydrogen gas? Well, I need this to, I need my second reactant to cancel out so that I'm left with my first reactant. Well, if I look at trial 1 and trial 3, if I would use those 2 trials, when I divide, this is going to cancel this out. Using 1 and 3, the value for trial 3 is larger, so I want to write that one first. Okay, so trial 3, the rate is 0.00486 molarity per second equals K times 0.60 m to the x, because we don't know what that is yet, times 0.30 m. And we can even go ahead and put our square up here because we've solved for that. Okay. Then trial 1, 0.00243 molarity over second equals K. Okay, on trial 1, I have 0.30 m to the x and 0.30 m, and I know my order now is second. Okay, I'm going to divide both sides. Okay, so this cancels out, my K cancels out, these 2 both cancel out. So I can rewrite my equation much simplified. 0.00486 divided by 0.00243 equals, all I have left over here is 0.60 m to the x over 0.30 m to the x. If I do this, I end up with 2.00 on the left and 0.60 over 0.30, my m, m and m to the x, these now cancel out. 0.3 or 0.6 divided by 0.3 is 2.0. So I have 2.00 equals 2 to the x. Well, the only way for this to be true is for x to equal 1. So now I know my hydrogen gas is to the first order. Okay, so hopefully that made sense. Again, I needed to find the order for my hydrogen, so I had to find 2 trials where my nitrogen would cancel out when dividing. So that was trial 1 and trial 3. to make life easier for myself, I chose to write trial 3 first because its value is larger than trial 1's. That way I'm dealing with whole numbers and not fractions. Okay, and in your homework, obviously these numbers aren't, in the real world, aren't always going to work out perfectly like these examples are. But for our class, Jay-Wah is going to give you numbers that work out nicely like this. Okay, so now we know both the orders. So now all we need to do is find the rate constant. That's the only thing that we still don't know. Okay. So to find the rate constant, we only have one thing that's unknown, because now we know this x equals 1, the y equals 2. We figured that out. We know a constant, we know these concentrations, and we know a rate. So pick any trial. It doesn't matter which trial you choose. So let's just look at trial 1. Okay, for trial 1, the rate is 0.00243 molarity per second equals K, which is what we don't know. Our concentration of H2 is 0.30 molarity. That's going to be raised to the 1. 0.30 molarity. This is raised to the second. Okay, so let's see if I've done this math out. So 0.00243 molarity per second. If I multiply these things, I end up getting K times 0.027 m cubed. Because remember, here I have 1m, here it would be m squared. So when I multiply this out, I would get m cubed. So then if I divide both sides, K ends up being 0.00243 molarity per second divided by 0.027 m cubed. And if I do that out, I end up with 0.090, 1 over, okay, I have a molarity over molarity cubed, so that would leave a molarity squared in the denominator times second. Okay, and a way to check this is our overall order is 1 plus 2 is 3. And our exponent should always be 1 less than the overall order, which it is. Okay, so that worked out nicely. Okay, there's another example in the book running through this exact same example 15.3. Nothing has changed. It's just another example to show you how to find the orders and how to find the rate and all of that. I guess I should have written down here then at the very end, the rate equation for this reaction would be our rate constant, which is the 0.0901 over m squared seconds, times the concentration of the hydrogen gas to the first order times the concentration of the nitrogen monoxide raised to the second order. Okay, so this would be my final answer. Okay. Again, there's another example 15.3 in the book where you can walk through another whole problem like this for more practice. And then obviously there'll be some in your homework too. All right, and that's where we're gonna stop today. Okay, so this coming week, you'll end up going through Comprehension Check 5. There's no lab. You'll have your test for Chapter 14. And yeah, let me know if you have any questions. Hope it goes well for you. Thanks.